Okay, good afternoon. This week we're talking about streams, which are an alternative implementation of the idea of a sequence. So far we've seen two different implementations of sequences, namely lists and vectors. And remember we said the difference between them was one of efficiency. Certain things were more efficient with lists, and other things were more efficient with vectors. Now we're going to look at a third implementation of sequences and find out about its efficiency properties, which are pretty cool. So we are here. Okay, so behind me on the board, I guess I should put it up so I'm not in its way. Behind me on the board is the definition of a prime number. An integer n is prime if it's greater than 1, and it has no factors other than itself and 1. Saying that another way, it has no factors in the range of numbers from 2 to n minus 1, right? So here's a helper procedure called range. And what range does is return a list of the integers between two values, starting and ending value. So using that, I have a predicate prime question mark that takes a number n. It constructs the set of numbers where we don't want it to have any factors, so the range from 2 to n minus 1. And then we say, filter that list of numbers with the predicate is the remainder when we divide n by x 0, which is how you say, is x a factor of n? And then finally, we say, is that set we got from filter empty? So if it's empty, then there are no factors between 2 and n minus 1. And we can see that, in fact, if we ask if 6 a prime, it says false. If we ask is 7 a prime, oops, 7, 5 would have worked too. Let's pick an odd number that isn't prime just to make sure that works. Everything is fine. Okay, so prime works. And it works in a way, I want to claim, that really precisely models the mathematical definition of a prime number. So you can read this code, these 3 lines right here, and say, OK, I'm picking out the factors of n in the range 2 to n minus 1, and I'm asking the question, are there any or not? If there aren't any, it's prime. Okay? However, there's a problem with this algorithm. That's this. Let's find out if 1,000,000 is prime. So while we're waiting, you tell me, is 1,000,000 prime? No. How did you know 1,000,000 isn't prime? It's even, right? It's divisible by 2. Oh, not only did it take a long time, we didn't get an answer at all. Let's try again. We'll ask if 100,000 is prime. So what it's doing is creating a list. Whoa. Man. This used to work. Sorry? No, I've always done it locally. I just used to have a real computer instead of this one. You know, that one back there. Ah, okay, 10,000 isn't prime. All right, so we ask about the primitude of primality of large numbers, large even numbers. And it generates this huge list. The reason I was getting segmentation fault is it's making a list of length 1,000,000 or a list of length 100,000 minus 2. Right? So for 1,000,000, it's 999,998 numbers in the range that we're interested in. Then it's going through that entire list, asking each number, are you a factor of 1,000,000? And it gets a whole bunch of factors of 1,000,000, 2 and 5 and 10 and so on. And then it says, is that list I got empty? And the answer is no, it isn't. But that's very, very inefficient. And so therefore, getting to the punchline, therefore, people tend to write programs like this one. So now I can say prime 6, no, prime 7, yes, prime 1,000,000, no, it's not. Okay? Now, if I ask, is 1,000,003 prime? It's still going to take a while to come up with an answer. Okay? If the number is prime, then we still have to check all the possibilities. While we're waiting, yes it is. How does this program work? Well, it has a helper function called iter, whose argument is a candidate for being a factor of n. And down here we start out with factor being 2, because that's the smallest number that counts for making something not be prime. And what iter does, it says, have we reached n? Is factor equal to n? In other words, have we tried every possible factor but from 2 to n minus 1? If so, n is prime. Otherwise, is n a factor of, is factor a factor of n? If so, then the answer is false, because we found a factor between 2 and n minus 1, so the number isn't prime. Otherwise, call iter with factor plus 1 as the argument. Okay? So everybody agree that this program works? Yeah. And this is the one you wrote in junior high school. Yeah. Yeah. He says, couldn't we optimize by only checking up to the square root of n? And yes, that's true, and it's pretty important actually, because the square root of 1,000,000 is quite a bit less than 1,000,000. So yeah, that would make a big difference. I didn't do that for any of these versions that I'm showing you, just to keep things simple. So yes, all of the versions that we're looking at could be optimized by checking only up to the square root. Okay? Okay, the problem with this version that's on the screen here, I want to argue, is that it's not very easy to read. I mean, because its name is prime question mark, you know what it's trying to do. But if it were named mystery, and you saw it on a midterm saying, you know, in one sentence, what does this mystery procedure compute? It would take you a while to figure out that it's checking to see if n is a prime number. Okay? Certainly, it would take you a while to be sure that it really succeeds, that You know, it doesn't mistakenly check for 1 being a factor or not check for 2 being a factor or something like that. It's just a lot harder to read, I think, even though it's more efficient. So I want to have my cake and eat it too. It's what computer science is all about, being immature and wanting to have your cake and eat it too, and figuring out a way to do that. So here's what we're going to do. Wait. Yeah, I'm in the right window. Helps if you spell it right. Okay. So this version looks exactly like the first version I had, except that the word stream is thrown in here and there. So it says stream null of stream filter, same filtering predicate, stream range, same arguments. All right, and now if we load this, I can now say, oops, stream prime, question mark, of 1,000,000, and get false right away, or any number you like. False. And of course, for small prime numbers, we can try it on like 17. It says true. And for the same reason as before, I'm not going to try on a large prime number because, you know, we'll get in trouble. Well, let's do try it on a fairly large prime number anyway. What did it failed on 100,000 before, right? Let's see what happens. Whoops, I didn't mean that. Okay, so this version succeeds. It doesn't say segmentation fault. So what I've done here is write a program that essentially looks like the one we started with, the one that made the list of all the factors. Here we're making a stream of all the factors, and then it picks out the ones that actually are factors of n, and then it asks the question, is that result empty? So it works, it looks like the first version, and yet it has a running time like the second version, namely instant for composite numbers with small prime factors, and doesn't blow up for large primes. Okay? How is that possible? Streams, by the way, work just like lists. So here's cons stream, and we also have stream car and stream cdr. If I show you the definition of stream filter, you can see con stream, and then stream car of data, and here's a recursive call on stream cdr of data. Okay? So cons car and cdr, just like lists, and yet it has this very different behavior. Why is that? How do we make this work? Well, let's see what happens when I say, well, first of all, let me just remind you about range 3 to 8, gave us this list. Now I'm going to say stream range from 3 to 8. And I get something different. What I get is, I'm going to just abbreviate by calling it range, even though for chalkboard purposes. Range from 3 to 8 gives me a pair whose car is 3. So far, just like a list. And then, where the next pair of the spine of the list should be, is a promise to compute the range from 4 to 8 later on. Okay? So this cloud-shaped thing, that's supposed to look like a cloud, is a promise. And you can see it's actually called a promise in STK. And what it says is, if you call stream cdr on this stream, then you're caching in the promise. And I will do whatever the promise says when you do that. That's how the promise gets cached in. You ask for stream cdr of this stream. Now, does that mean that if I ask for stream cdr of stream range 3, 8, am I now going to get the list 4 through 8? No. I get a pair whose car is 4 and whose cdr is a promise to compute the range from 5 to 8. So each time you cdr this stream, you get one more element plus a promise. Is that clear? Everybody understand that? I know you don't know what a promise is yet, but you get the idea of what a promise is for, right? Any questions? Yeah. What about when you get to the end? So the base case here in stream range says if from is greater than 2, which means we've run out of numbers to pick, return the empty stream. It's a thing. Streams are an abstraction. Okay? So just like lists, in the list abstraction, to make lists work, we have to provide two things. One is pairs, and the other is a thing called the empty list. So for streams, it's the same business. We have pairs whose cdrs are promises. Right? For lists, it's a pair whose cdr is a list. For streams, it's a pair whose cdr is a promise, presumably also to compute a stream. And there's this thing called the empty stream, which is how you know you got to the end. Okay? Okay. So why does this speed up finding out whether 1,000,000 is prime? Well, what I do, so remember it's stream filter, some predicate, right? Lambda something, and then stream range from 2 to n minus 1, whatever that is, right? Yeah? Well, we call stream filter. We have to evaluate these arguments. We evaluate the lambda expression. We get a procedure. We evaluate this call to stream range, and we get a pair whose car is 2 and whose cdr is a promise to do stream range from 3 to n minus 1. Right? Now, that's a value that was computed in essentially no time. Right? Constant, small constant time, because we're only really looking at one element. That's what we give as the argument to stream filter. Now, you remember how filter works, right? It says, is my input empty? If so, return the empty list. Otherwise, there was a three-way con clause. The next clause says, does my car satisfy the predicate? If so, cons the car onto a recursive call to filter. If not, then just do a recursive call to filter on the coulter. Okay? Well, the predicate says, is the car a factor of 1,000,000? Yes, it is. So what does filter return? A pair. Because stream filter calls const stream. So we're going to have to talk in a bit about how const stream works. But what it returns is 2, because yes, that's a factor, and we're collecting all the factors of 1,000,000. And a promise to do filter, stream filter, of this function over the thing that promise promised, right? Stream range 3 to n minus 1. Okay? That's what we're promising to do. Stream filter returns this. Stream filter's finished, at least for now, because it found one element of its output, and it's only promising to do the rest later. So it hands this to stream null. Does stream null have enough information to know whether or not this is empty? Yeah, it does. This is not empty. It has at least one element. So even if 2 were the only factor of 1,000,000, we already know that 1,000,000 isn't prime. Okay? So stream null is going to be perfectly happy having found one element, and therefore is never going to cache in the promise to look at the rest of the elements. So all those promises are just going to be unused. And that's why streams can do the job quickly. Right? Yeah? Yeah, good question. Let me reword your question by going back to stream filter and looking at this right here. So stream car satisfied the predicate. 2 was a factor of 1,000,000. So we do this. Well, when you call a procedure, first we evaluate the arguments, because scheme is an applicative word or a language, right? So first we evaluate the arguments. And one of those arguments is the recursive call to stream filter. And that calls stream coulter to get one of its arguments. So aren't we going to cache in this promise right away, is what you're asking. Why doesn't that happen? That's a very good question. And the answer is it doesn't happen because, and this is the entire secret of streams, cons stream is a special form. Okay? Everything else here is just regular old stuff. But cons stream is a special form. And even special forms, you've seen special forms before. I mean, they're different, but they're not really deep magic, you know. They just don't evaluate their arguments until, you know, they decide whether they should or not. So the way it works is if you say cons stream AB, the evaluator sees, oh, cons stream, that's a special form. In fact, it's an abbreviation. The way let is an abbreviation for something, it rearranges things syntactically. Cons stream is an abbreviation also. What it abbreviates is cons, plain old cons that makes a pair, A, because we want the stream car to just be what the car would have been, and then delay B. Okay? Now, cons stream is not a scheme primitive. It's something that we added to do the stuff in the book about streams. Delay, however, really is part of scheme. It's built into scheme, but I'm not allowed to say it's a scheme primitive because it's not a procedure at all. It's a special form. So delay is a built-in special form that takes any expression and returns a promise to carry out that expression later. So delay expression returns a promise to do expression later. Okay, is that clear? And that's why I'm finally answering your question. That's why stream filter returns right away, because it does con stream rather than cons, and that means the recursive call, the thing that's the second argument to con stream, is delayed. So we just make a promise to call stream filter later. Okay? Everybody happy so far? Okay, so I want to back up here a minute and look at this, sort of the important procedure of this example. And I'd like to make sure you really appreciate what it is that we've done here. With very little in the way of underlying mechanism, basically just delay, we have decoupled the sequence of events in the computer from the algorithm as laid out in the code. Okay? So according to this code, we get the whole range of factors, of possible factors, from 2 to n minus 1. That's what this code says. Give me the range from 2 to n minus 1. Okay? Now, according to everything we've known up to now, that means we have to sit and wait while we generate a big list of numbers. The actual sequence of events in the computer is much more like that second version I showed you, the iterative one that didn't make all the factors in a list but just made them one at a time. That's what we're doing. We're coming up with factors one at a time to try out. Yeah? How would you calculate the running time of this, the order of growth of running time? The worst case running time is sort of the same. The worst case is you have a large prime number, in which case it's basically theta of n, because you have to check every value to find out that it isn't a factor before you can say conclusively that this number isn't prime. Now, as someone over there said, we can make it theta of square root of n, which is a lot better, because if a number doesn't have a factor less than its square root, then it doesn't have a factor bigger than its square root either. Okay? So worst case, theta of square root of n for doing it for any version of, no matter how you write your prime program, there's no getting around the fact that you have to try all those things. Well, that's not true. The book points out, in a little bit of heavy mathematics that some of you won't like, but the book points out that there are some interesting ways to find out if a number is prime that almost always give you the right answer and are very fast. Almost always, meaning really almost always. The book says the probability of getting a wrong answer through this algorithm is smaller than the probability of getting a wrong answer because a cosmic ray happens to strike your computer at the wrong moment. So it's really very good. But it's not perfect. It's not mathematically, Anyway. If the number is composite, then the running time will be theta of its smallest factor, other than 1. Right? So some primes, some composite numbers, sorry, they have exactly 2 factors other than themselves in 1. And both of those factors are huge 80-digit prime numbers. So it's really very difficult to check whether that number is prime or not. numbers, composite numbers like that are the product of two very large primes, are at the heart of modern cryptography. Basically, you tell people one of the factors, or no, you tell people the product. That's right, but you don't tell them the factorization, and you need the factorization to decode your message. Okay? Okay, well, that was a little bit off to the side, but no, it's not. It's important for you to know, I guess. But let me restate one more time, because it's really important. What we're doing is decoupling the sequence of events in the computer from the form of the program. So this is an amazing piece of abstraction, right? In essence, you're telling the computer to do one algorithm, and the computer is saying, no, I can do this faster than that. I'm going to use this other algorithm. And yet, I promise to get the same answer. And you don't have to worry about it. That's really amazing. And the mechanism to do that is just delaying the evaluation of one argument to cons. By the way, how does delay work? Delay is built into Scheme. So you might think of it as, you know, a piece of complicated magic. But we're going to implement delay, version 1 of delay, as, again, a syntactic abbreviation. So I'm going to translate delay expression into something else. What I'm going to translate it to is lambda, no arguments, expression. That does it, right? Because when you see a lambda expression, do you evaluate the body? No. You don't evaluate the body until you call the procedure. So the opposite of delay, by the way, is called force. That's not a special form. It's an ordinary procedure. So we say define force of some promise to be, call that promise. Right? Because the promise is a lambda expression with no arguments. We can invoke it. Invoking it evaluates its body, which is the expression that we were delaying before. Everybody see that this works? Any questions about that? Yeah. Okay. Suppose that the number that we have isn't divisible by 2. Let's say we want to know if 9 is a prime. Okay? So we make, maybe I should actually draw this out. So I want to know if 9 is prime. So I'm going to make the range from 2 to 8, okay, which is 2, and then a promise to do range from 3 to 8. Yeah? Now I'm going to give this to filter. Filter's going to say, is this empty? No, it's not. Does stream car of it satisfy the predicate? No, it doesn't, because 2 is not a factor of 9. Else, it says in stream filter, I'm going to make a recursive call to myself with the same predicate and stream cdr of my argument list, my argument stream. Right? So it does a recursive call to itself, having called stream cdr. Stream cdr forces this promise. So stream cdr, and this is happening during the call to filter. None of this is delayed, because the delaying only happens in constream, and we only call constream if we want to keep this value. In other words, this value is a factor. As long as it isn't a factor, stream filter keeps on doing recursive calls in the same way that filter does recursive calls. Okay? So we try again. We take the range from 3 to 8, and that is 3 followed by a promise to do range from 4 to 8. Stream filter says, is 3 a factor of 9? Aha, yes it is. So this is what stream filter returns. Okay, does that answer? I forget whose question it was. Does that answer the question? Yeah. Okay, good. We only barely have time to get to the crucial next step. Oh no, before I get the crucial next step, I have to point out something else. I've been writing on the board things like when you do range 2, 8, you get a promise to do range 3, 8. Well, if we look in the actual con stream here in stream range, and the important part of it actually is this, here's what we're going to promise to do. This doesn't say stream range 3, 8. It says stream range plus from 1, 2. Well, when I force this promise, it can be some completely different world. How do I know what from and to means? Well, that's a lucky side effect of lambda, because you now know from the evaluation model of environment that lambda creates a procedure, and what the procedure is, I'm running out of boards already. What the procedure is 2 bubbles. This one basically is just a pointer to the expression, because there aren't any arguments, right? But what is this? It's a pointer to an environment. And guess what? We have from is 2, 2 is 8, okay? And the expression in this case is stream range plus from 1, 2. Okay? And all of this is the promise. So promises carry around with them the correct values of variables for this particular promise that we're making. And that just exactly does what we need. So it's important to understand that too. Okay. Now for the fun part. I need, from this colored chalk collection, a couple of colors here. So here's define range from 2 if greater than from 2 empty list. Otherwise, cons from onto range plus from 1, 2. Close range, close cons, close if, close define. Okay? That's the plain old range for plain old lists. So here are the changes we made. We changed the name. We changed this to the empty stream. We changed cons to con stream. And we called it with. Okay? So the change of name, that doesn't do anything really. That's trivial. We could have kept it the same name. I just wanted to have them both around at once. To let you in on a secret, the empty stream is actually the empty list. We could have used anything. It's just being compared against, but we used the empty list. So really this isn't a change at all. The only actual change that matters is this little thing right here. So we made this teeny tiny little change to the program, and it had a huge, huge, huge effect on the program's behavior. Right? Now, we're going to do something different. I'm going to do this. Recursion without a base case. What should happen? Infinite loop, right? Looks like a disastrous change. Let's go ahead and do it. Except I'm going to change the name. And because I'm not doing this base case test anymore, I never use the argument 2. So I'm just going to get rid of that also. And I'm going to say constream from ints from plus from 1. Whoa. What does that do? Essentially nothing, interestingly enough. I say ints from 1, and I get an answer, which is 1 dot a promise to do ints from 2. So I'm going to actually just, for ease of use, define integers to be ints from 1. And now if I look at integers, I get this unedifying thing. But we have something called showStream that takes a stream as argument, and it does this. It gives you, if there are fewer than 10 elements, it just looks like a list. Otherwise, it gives you the first 10 elements and then a dot, dot, dot. Okay? So you can see what you've done here. You can also say, oh, there's an abbreviation for showStream. It's SS. It takes an optional argument where you can say how many values you'd like to see. Okay? So that's the integers. We have all the integers in our computer. I can say showStream stream map lambda x times x2 integers. And what I get is I don't have a parenthesis. There we go. I get all the even integers. Okay, so we can do arithmetic on an infinite data set in no time. In this tiny little box, I have all the integers. That's pretty amazing as an abstraction. Okay, we're going to do something even more amazing. It's called the sieve of Eratosthenes, and works like this. You write down all the integers starting from 2. This is going to take me a few minutes. No, I'm kidding. That's enough. And then what you do is this. Here's the algorithm. Circle the first otherwise unmarked number. It's prime. Now cross off all its multiples. Did I get them all? I think so. Repeat, just like shampooing. So take the next unmarked number, that's 3. Circle it, it's prime. Now cross off all its multiples. Okay, some of them we crossed off twice. It doesn't matter. Okay, repeat. Find the first unmarked number. Circle it. It's prime. Cross off all its multiples. Basically, that's all I have to do. The rest of them we all got already. Circle the next number. Cross off all its multiples, of which there's only one left, 49, because all the other ones are 7 times something smaller than 7. So we've got them already. And that's it. All the rest of these numbers on the board here are prime. Okay, that's the sieve of Eratosthenes. So what does this say? So we take stream-Kutter of integers, because integer starts with 1, which doesn't count for primality. We want to start with 2. And we call sieve. Sieve takes a stream of all the numbers that haven't been crossed off yet, basically. It says constream the first number. That's like drawing a circle around the first number. We keep it. It's prime. And then we do a stream filter on the stream-Kutter of the stream, where we say, take out all the ones that are divisible by the stream car. And then we just recursively call sieve on that. Okay, so that's an infinite recursion. And here they are, all the prime numbers. All right? That's a pretty amazing piece of computation. And how we got there is by understanding abstraction, basically, by saying we can take the idea of a sequence and we can implement it in this completely different way. And also by understanding something else, which is normal order evaluation, because that's basically what a special form does. Right, so constream, well, it's kind of a hybrid. It uses applicative order for its first argument. You could write it the other way if you wanted. But it delays, which is to say it normal order evaluates its second argument. It doesn't evaluate it until somebody needs it, until somebody calls stream-Kutter. Okay? So this is just an incredible result that I can't get over it. Every time I see it, it's amazing. All the prime numbers. You want to see some more? Wait. There. Okay? All right. See you Wednesday.